them out in black and white, because last time I printed them out in color, I got shouted at. Unfortunately, quite a lot of what we do with lighting requires sort of us to be able to see sort of subtleties in color. So the printed notes aren't ideal. So I would recommend actually checking out the notes which I put up on Moodle, which have got all the figures in color. Okay, so this is direct lighting model. This is chapter 6 in the printed notes. Okay, so essentially, what is the need to actually have lighting in graphics? Well, if we think about three-dimensional objects, the way we can tell objects, the way we get visual cues about their shape and their geometry is by how light and how shadow appears on the object. Now, what I've got on this slide is Newell's teapot. Quite familiar with this by now as part of your hidden surface removal assignment. Now, I've plotted the same teapot. Okay, these two figures are of the same object. Okay, this figure on the left, this is a three-dimensional teapot, which I've just colored in all the polygons red. Now, as you can see, it appears flat. We've got no idea about the shape of the object or what the sort of geometry of it is, or what the surface is like. Okay, this plot on the right is exactly the same object. Okay, it's not, you know, that one there is a 3D object, but we just can't tell. This one on the right is exactly the same object, but I've included lighting on it, and straight away we can tell, but it sort of, we can tell that it sort of bulges out. It's a 3D object. We can tell it's got a lid and a little handle, etc. Okay, so obviously the one on the right is a much better image than one on the left. So that's what we're going to be looking at today. We're going to be looking at how do we add lighting to our graphics, in other words. Now, there are two main models of lighting. One is called a global model. Now, a global model takes into account light from light sources and from bouncing off all other objects. So global, or often called global model, uses what we call indirect illumination. So this is sort of summed up in this diagram. So if I have a light source here, one key thing which we're going to assume is that light travels in straight lines. Okay, light doesn't bend. Now, talk to a physicist and they'll immediately argue about that, but we're saying, okay, we're assuming that light does not bend. Okay, and when light falls on an object, you don't actually see, when you see an object, you're not actually looking at the object. You're looking at what light is reflected off of that object. Okay, so for example, over here on the left, a light source will hit an object, light reflected from the object into your eye, and therefore you see the object. So looking at these chairs, you're seeing the light which comes from these lights in the ceiling and some lights from the door. Okay, you're seeing the light bounce off the chairs and going into your eye. Well, into your eye, it falls on the retina at the back of your eye. So that's what we call direct illumination. So light goes straight from a light source, bounces off an object, and goes into your eye. Indirect illumination is when light source bounces off an object and then bounces off another object, or multiple times. Okay, so this is direct. Indirect is when it reflects off other objects and eventually gets to your eye. This is simple to do, direct illumination. Indirect illumination is difficult to do. For example, ray tracing. Have you ever heard of ray tracing? Okay, that's if you look at Pixar films and any form of like CG films like that, they would use indirect illumination because they've got time to actually calculate it all. In something like a virtual world or a computer game, you haven't got that time. So they tend to use direct illumination, but we have a few tricks to allow us to sort of mimic indirect illumination. Okay, so this is what we're going to focus on. We're going to focus on light source hitting an object, going straight to the viewer. We could, if we had infinite computational resources, actually use indirect illumination, but we're not. Okay, that's a difference. Global illumination uses indirect as well as direct. Okay, direct only uses direct. Okay, what I'm gonna present to you today is a reflection model called Fong's reflection model, and this uses 3 components. And the first component is what we call ambient reflection. Now, ambient reflection is defined as the reflection of light that does not come directly from a light source. So if you look in the ceiling, we've got a number of light sources. Each of those light bulbs in the ceiling is what we call a light source. If I was to turn off the lights in here, yeah, why not? Why not? Don't I? I'm just going to turn off the lights. Okay, unfortunately, we've got the projectors and we've got the lights coming in from outside. But if I was to turn off all light in here, you'd still be able to make out rough shapes. Okay, and the reason for that is light bounces off of other objects. Have you ever heard of night vision glasses? If you've seen sort of nature programs or something like that, you've got glasses which can take in tiny amounts of light and still be able to sort of detect outlines. Okay, so what I mean by that is light bounces off of other objects. So even in a darkened room, we still be able to make out sort of rough outlines. Okay, what ambient reflection is a model of this. Okay, so what we do is we create a Phong model which uses ambient reflection, which is an approximation of an indirect illumination. Okay, so we assume that ambient light falls equally on all objects in our scene. So rather than calculating, okay, light's bouncing around this object onto this object, etc., we say, oh, sod that. We're just going to say all objects in our scene have equal amount of ambient light falling on them. Mathematically speaking, what we could do is we can use this to model it. Okay, A is the amount of ambient reflection. IA, that stands for the intensity of the ambient light. How bright is your ambient light? And Ka is the ambient coefficient. How much of ambient light are we using? So I is intensity, K is the coefficient, how much? So if K is close to 0, we've got a very dark scene. Okay, all objects within your scene have hardly got any ambient light, so it's very, very dark. If K is close to 1, then you've got a very light scene. Okay, so all objects have got lots of ambient light falling on them, so it's very bright. So that's the first part of our model. Okay, our ambient reflection. In the notes, this doesn't come out very well. Well, what I've done here is I've drawn our 3D teapot using different values for the ambient coefficient. Okay. So if Ka was 0, this would be a black screen and we couldn't see anything. Okay. So if Ka is a quarter, okay, I have a blue teapot here, and it's kind of looks kind of dark. As I increase Ka, which is our coefficient, okay, you can see the teapot gets lighter and lighter. So when Ka equals 1, this is the actual object color of the teapot. So your Ka, that determines how, generally speaking, how light or how dark your scene is. So let's say you've got a nighttime scene. You'd set Ka to be quite small, and so therefore you can't see many objects. If you've got a bright daytime scene, you'd set Ka to be closer to 1, so you've got bright objects. Okay, that's ambient reflection. Notice, you've got to believe me on this one, this is a 3-dimensional object here. Ambient reflection doesn't give us any idea whether that object is 3-dimensional or not. Okay, all it does is just increases the color of the object. Okay, so then this brings us to the second component of our lighting model. This is called diffuse reflection. And diffuse reflection is the reflection of light off of rough surfaces. If you've got a rough surface, they'll often look dull. Okay, so for example, I'm looking at these chairs. these chairs have got a fabric covering. Okay, that's quite a rough surface. And so they kind of look like a dull object. Okay, so what's happening is if we got our surface here, I've just sort of drawn a rough surface. As incident rays hit our surface, so these are parallel incident rays, so these will come from a light source. As they hit the surface, they're scattered in all directions. Okay, so depending on where you are, where you're viewing the object from, you might see some reflective rays, you might not see others. Okay, so this is the idea of reflection off of a dull surface. And this is what we call diffuse reflection. So how do we model this? Okay. We could, if we had lots of computational resources, we could have the surface defined. Okay, there'll be lots of vertices along the surface. Calculate, okay, where are these reflection vectors going to be? And then calculate each individual incident ray. Okay, unfortunately, that's far too much work. Okay, we need to cut down on the amount of work we do. So what we do is we assume that all of these these reflected rays is reflected equally in all directions. Okay, so this is our model of diffuse reflection. So if we have a light ray, the reflected rays are scattered equally. The magnitude of the reflected rays depends upon the angle that you're viewing the surface at. Okay, so here I've got 4 diagrams. I'll just explain what these are. Okay, so I have a surface. This is my surface, okay, and I have a normal vector to the surface pointing perpendicularly away. Okay, the light source vector is this one. So it's a vector pointing from the surface to the light source. Now, I've used the vector pointing in this direction because that's what is mostly included in the literature. Some people actually have the light source vector pointing towards the surface. Doesn't matter, all you do is you just change the sign of the vector. So that's why it's pointing from the surface out, because that's what's mostly used in the literature. Okay, well, it's quite hard to see here, but we have an angle. The angle between the light source vector, L, and the normal vector are called theta. And when this angle is quite small, the reflected rays, or the length of the vectors of the reflected rays, is quite large. So when you're looking at an object or a surface sort of face on, the diffuse reflection is quite large. As the angle between the light source vector and the normal vector increases, so theta here is increasing, what we have here is we're reducing the size of the reflected rays. So those rays are reflecting in all directions, we've just reduced their size a bit. So here, on the one on the bottom right, we've got quite a large angle, almost 90 degrees. Okay, so the angle between the light source vector and the normal vector is quite large, so we've got quite small magnitudes of our vectors. Okay, until if the light source and the angle between the light source and the normal vector is 90 or more than 90, okay, if it's 90, light coming from this light source does not reflect off the surface at all. So there's no light reflected. If the light source is down here, of course there's not going to be any light reflected because the light source is behind, and that will be in shadow. So this is how we model diffuse reflection. So the angle between the normal vector and the light source vector determines how much light gets reflected. Okay, so this is our diffuse model. Okay, slightly more complicated than the ambient model. So I've used D for diffuse. IP is the intensity of the point light source. So if you look at one of these bulbs in the roof, okay, that will have an intensity. That's what IP is. With the ambient light, it was IA. Okay, well, that is ambient intensity. IP is different. IP is your point light source intensity. How strong is your light coming from a light bulb? So let's say you're doing some lighting for a scene and it's lit by a candle. You might reduce IP so it's smaller than, for example, if it was lit by a light bulb. KD is a diffuse coefficient. This is the same as KA was for ambient lighting. So that's KD is a coefficient between 0 and 1. You set that to how much diffuse reflection you want for this object. If your object is very shiny, you might not have much diffuse reflection. If your object is very rough, for example, like a carpet, you might have a lot of diffuse reflection. So that's kind of like a tuning thing. And this, okay, this deals with the angle between the light source and the normal vector. So theta is your angle between the light source and normal vector. Cos theta, okay, why have I used cos? Well, when theta is 0, cos theta is 1, okay, and when theta is 90 or pi over 2, cos theta is 0. Okay, so cosine of this angle gives us our relationship for the length of these vectors. Okay, maximum between cos theta and 0. Well, we never want this to be negative, so that's why we've got maximum between cos theta and 0. Okay, and that's used so that no light is reflected if the light source is behind that surface. Okay, we've got a problem here, and I keep banging on about it, is graphics, we need things to be computationally efficient. Okay, these calculations are done thousands of millions of times a second. We need them to be efficient. Cosine is an expensive calculation. Okay, we calculate it using series, Maclaurin series, for example. Okay, we don't want to have to do all that work. So what we can do is we can use dot products. So just to give you a bit of refresher, okay, here I've got two vectors, A and B, and theta is the angle between them. Definition of dot product is A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. We need that cosine. That's what we're trying to calculate. That cosine theta, that's what we need. If A and B are unit vectors, then the magnitude of A will be 1 and the magnitude of B would be 1. So this would be, if A and B are unit vectors, we'd have A dot B equals cos theta. So if L and R, if L and N are unit vectors, then L dot N would just equal cos theta. So instead of having to calculate the cosine, quite simply, all we do is calculate the dot product between the light source vector and the normal vector. And this is our model for diffuse reflection. Okay, so what's it look like? Well, here you go. This is the same teapot as used before. Okay, and all I've done here is I've set the ambient light to be, I think I've set it to be something like a half. Actually, probably closer to 1. All I've done is set the ambient light so it's constant, and I've moved the KD up a bit. Okay, so KD goes between 0 and 1. When KD is 0, you've got no diffuse reflection. So it just looked like a flat teapot would just look flat. So when I've got a little bit of diffuse reflection, you could just start to make out a bit of shadow and a bit of sort of brightness around here. Okay, so when KD is a half, you see a bit more of the teapot. Okay, so the lit bit, so the bit reflecting is a bit bigger. Okay, as KD goes larger, in my opinion, you tend to sort of almost wash out the teapot. So KD controls how much light is being reflected or how much diffuse light is being reflected. In my opinion, this probably KD is 0.75 is a bit too much. I think this one probably looks the best. Okay, if we're trying to represent a teapot, you set your KD to be what's best for that object that you're defining. So that's diffuse reflection. So ambient is light bouncing off of everything and light falls on everything in the same way. Diffuse reflection, that depends upon the surface and what angle you're viewing the surface at. So for example, this front of this teapot here, we're probably viewing it straight on, so we see a lot of light. As the surface sort of bends around a bit, we're seeing less light being reflected off of the side. so therefore it's darker. Okay, and the last component for our model is specular reflection. So this is reflected rays off of a shiny, smooth surface. And reflected rays off a shiny, smooth surface reflect an angle which is the same as what it hit it. So I'm assuming you all know what mirrors are. I'm judging by some of you, maybe not, but sorry about that. I do that joke every year, but there we go. So this is what we have. If we have parallel rays, incident rays coming in and hitting at a flat, smooth surface, we get parallel reflected rays reflecting off. Okay, so rather than diffuse reflection, scattered rays in all direction, specular reflection scatters them in one direction. Okay, so in order to form a model of specular reflection, we need, well, we got the surface normal vector n. Okay, so this is my surface, this is my normal vector pointing perpendicularly away, and this is our light source. So if this is a light source vector and the angle between the light source vector and n is theta, then r is a reflected vector. Okay, and the angle between n and r is also theta. So basically it means the angle of incidence is the same. The reflection vector is the same as the angle of incidence. Okay, we've also got another vector called a viewing vector v. Now this is a vector that goes from the viewpoint to the surface. Now when we look at when we look at a shiny object, we're not always going to be looking along the reflecting vector. But just because we're not looking directly down r doesn't mean we can't see any shininess. Okay, so we have another angle which I've called alpha. And this is the angle between V and R. If V is close to R, that means alpha is small, and we should see reflection. We should see specular reflection hitting, sort of coming back to our eye. If V and R are far apart, that angle alpha should be large, and therefore we shouldn't really see much reflection. So it's like sort of tilting a mirror around. Okay, if you've got a mirror and you tilt it around, you'll see the light hitting the mirror and going into your eye. Okay, so that's what we're going to use for our model of shiny surfaces. Okay, and this is the model. What we have is we have the intensity of the point light source. That's the same as it was for the diffuse model. So IP is the same. So diffuse model uses, okay, we've got a light source coming from, for example, these bulbs. Okay, the specular reflection uses exactly the same one. Ks is a coefficient. Okay, that's a specular coefficient. That's in the range 0 to 1, and like Ka and Kd, that sort of tunes how shiny our object is. N is something new. Little n, sorry, this isn't the normal vector. This is a lowercase n. Lowercase italicized n. That's what we call a specular exponent, and I'll just mention what that is in a minute. That's sort of what's the spread of the light reflecting off of the shiny object. And alpha is the angle between r and v. Okay, so we have a cosine alpha that raised to the power n. Okay, why have we got that cos alpha raised to the power n? Well, Phong, who developed this in the early 70s, okay, he used this model. Okay, what I have here is I plotted along the horizontal axis, I've got angle theta. Okay, so that should really be alpha, really, but okay, I got theta. This goes from minus pi over 2, i.e. minus 90 degrees, to plus pi over 2. Okay, and on the vertical axis, I've got cos to the power n of theta. Okay, and for 3 different values of the exponent n, I've plotted the graph. So the blue one is when n equals 1. The red one is when power is 5. And the black one is when the power is 50. Okay, well, this is our model. This is how much shininess comes off of the object. Okay, if we want lots of shininess coming off of an object, we set n equals to 1. Okay, and we've got a nice wide sort of bits of shininess. If we want less, For example, we could set n equals 50, and then we've got very narrow sort of specks of shininess coming off an object. Okay, so that's what I mean by that. Okay, what I've done there is that's the teapot, and what I've done is I've plotted it so only specular reflection is shown. So notice the teapot doesn't look blue. This is because I haven't got any ambient light being reflected, and I haven't got any diffuse light being reflected. Specular light takes on the color of the light source. So I'm assuming the light source is white here. If I had like a red light, these sort of white areas would look red. So when you look in a mirror, you don't see the color of the mirror, you see the color of the light being reflected off of the mirror. Okay, so what we have here is different values for n. Now when n was 50, okay, we've got a very narrow band of light. So you can see here, I've set n equals 50. So where I've got specular light bouncing back towards my eye, I've got a very narrow band of specular reflection there. And what I've done, I've reduced the value of the exponent. So n is 20, so you've got a bit wider. Okay. So with n is 50, the only thing we could really see on the teapot is this sort of thing here. It's a tiny bit of the handle. You can't even see any of the spout. Okay. As I reduce n, we see a little bit more of the handle and a tiny bit of the spout there. Okay. And as I reduce the value of n further, we're widening the amount of the amount of specular reflection we're seeing. N equals 1 is a bit daft. Okay, you can see when we whack n equals 1 way up, that looks a bit too sort of unrealistic. Okay, so n equals 5 looks okay. So that's your specular reflection. Notice you're not seeing the color of the teapot, you're seeing the color of the light hitting the teapot. Okay, and that probably didn't appear very well in the printed notes, but that's what it should have looked like there. Okay, how do we calculate that reflected vector R? So diffuse reflection, specular reflection needs that vector R because that's the vector that's being bounced back from the lighting vector. And what we do is we use something called vector projection. And I'll explain what that is now. So here I have two vectors, A and B, and theta is the angle between them. Now the projection of A onto B, okay, if I drop this dashed line from A and it hits B, okay, C is the projection of A onto B. Okay, so it's what we call vector projection. I want to be able to calculate C, and this is going to be used to calculate our reflected vector. So definition of dot product. For some reason I've got alpha there, that should be theta. Okay. A dot B is equal to the magnitude of A times magnitude of B times cos of the angle between them. Well, the cosine of this angle here, cosine is adjacent over hypotenuse. The length of my adjacent side will be the length of C, which is here. And the length of the hypotenuse for this right angle triangle will be the length of A. So instead of cosine, I've got C over A. Now, of course, the A would cancel out with this one. Okay, so in other words, A dot B equals magnitude of B times the magnitude of C. So if I wanted the magnitude of C, which is the length of this vector, it's just A dot B over the magnitude of B. Now, let's say B is a unit vector. So B has a length of 1. Okay, if B has a length of 1, then the length of C is simply A dot B, because we've got A dot B over B. And furthermore, if we multiply B by the length of C, we get the vector C. So let's say B has got a length of 1, and let's say A dot B is around about 0.6. Okay, so if we multiply 0.6, because this A dot B is just a number, if we multiply 0.6 by your vector B, you get your vector C. This is vector projection. And this is assuming that B is a unit vector. How does that help us calculate reflection vector? Okay, so you've got this diagram in the notes, but I've sort of broken it down into parts on this slide. So there's my surface. That's my normal vector. I'm assuming that is a unit vector, okay, just to make the calculations easier. Okay, we have a light source vector L. Okay, we want to calculate the reflection vector R. So how do we do that? Well, using projection, okay, if we project L onto N using what we did in the last slide, okay, we have L dot N multiplied by N. So remember, we're assuming N is a unit vector. So this vector here, going up to this point, is simply the projection of L onto N. Okay. What I'm now going to do is I'm going to move N away just so it's not confusing our diagram. And what I can do is I can add R onto L. So all I've done is I've taken the vector R and I've added it to the end of the vector L. Okay. So we have this projection. If I add this projection onto itself again, we get to the same point. So what I mean by that is L dot N multiplied by N. If I add it on to itself again, I'm at here. Well, that's the same as L plus R. So I've got a relationship there. L plus R is equal to 2 lots of L dot N multiplied by N. Rearrange to make R the subject, and that's how we can calculate the reflection vector. Okay, so to calculate reflection vector, really complicated using Cartesian geometry. Very, very easy using vectors. It's just a dot product, some multiplications and a subtraction. Okay, so that's how we calculate the reflection vector, which is required in specular reflection. Okay, so we got in our model, in our direct model, so far we got ambient light, which is light bouncing off of all other objects. We've got diffuse light, which is light bouncing off of rough surfaces. And we've got specular, which is light bouncing off of shiny surfaces. Another thing we can take into account is what we call attenuation. This is loss of light energy over space. Okay, let's say you've got a dark scene and you've got a candle. That candle is not going to light up much. Well, it's only going to light the region around the candle. Okay, if you're far away from the candle, not much light from the candle is going to hit you. And we've taken this into account using attenuation. So we introduced a variable f subscript ATT. Okay, don't know why it's that. It's just what's in the literature, what Phong decided. And this is applied to diffuse and specular components. It's not applied to the ambient component. Okay, theoretically, by physics, it should follow the inverse square law. So if d is a distance from the light source, it should be proportional to 1 divided by that distance squared. So the further away you get, the less light you see. Okay, in practice, that removes too much light. So what we've decided to do is we use a simplified one. So d is a distance, r is the limit of the light source's sphere of influence. So r is, okay, how far away are we from the light source before we don't see any of that light? Okay, so this is just a proportion. So 1 minus this, and that gives us a good model for attenuation. Okay, so let's bung it all together. All we do with Fong's model is we add them all together. Okay, so this is the combined model, okay, of ambient, diffuse, specular, and attenuation models. Okay, so I is just what's the intensity. Okay, that was our ambient model way back on like slide 2 or 3. So that's the intensity of the ambient light multiplied by the coefficient Ka. All K coefficients are between the range 0 to 1. You just set that for whatever object you have. Diffuse, well, it's the attenuation okay, multiplied by the intensity of the point light source. So if we got one light, let's say only one of these lights in the ceiling was working, okay, that would be IP. KD, that's again the value from 0 to 1. And this max L dot N, that deals with the angle between L and N. Okay, so that's your diffuse model. Added to that, your specular, which uses attenuation, the same point light source as the diffuse model, a coefficient for the specular, again, that goes between 0 and 1, and V dot R to the power N, okay, that's an approximate, or that's your cosine of alpha to the power N. So instead of the cosine, we've replaced it with a dot product. Okay, so that's our Fong's reflection model. Okay, ambient plus diffuse plus specular. If you've got multiple light sources, so one look at the ceiling here, we've got a number of lights. What we do is we sum the diffuse and the specular parts. The ambient is going to be different. Ambient doesn't matter where what the point light sources are, it's the same. Diffuse and specular are summed for each individual point light source. So looking at the ceiling, we got about 12, let's say 14 lights there. We've got some light coming in from the doors, some light coming in from these projectors. Okay, so if we were to model or apply this model to this room, we'd have to sum, say, about 20 different light sources for that. And this is the result. Okay, so that's the teapot. Okay, the top left is just the ambient light, nothing else. So that's your ambient light. Top right is diffuse. Okay, so that's modeling your rough surface. Okay, remember you set your KD to be what you want it to be. Down here, specular. So notice specular only gives us those shiny bits. It doesn't give us any idea of what the color of the object is. It only gives us, okay, this is what light coming from the point light source, hitting the teapot and bouncing out. Okay, if we add them all together, we get our complete Phong model. So that's your model of direct lighting model for the teapot. Okay, just to recap, lots of variables. Okay, probably these are sort of things you just got to remember, really. But if you remember that I is intensity, K is your coefficient, FATT is attenuation, and you got your vectors N, L, R, and V. So it is a lot to remember, but it's not. They make sense. Oh, one thing I didn't mention is this lambda. This is just your red, green, blue components. So you'd apply this model for your red and your green and your blue. So you combine them all and add them all up. It's not something I'm going to expect you to do. I'm not expecting you to program this in. Okay, it's already been done in MATLAB, so it's not something I'd ever ask you to do. In fact, if you do get MATLAB up, it's got a command called material. So if you're doing a plot and you want to apply a certain type of material to it or certain shininess to it, use the material command. And this is a help file that comes up. Okay, they got some presets, for example, shiny, dull, and metal. Okay, I mean metal as in the metal, not metal as in the genre of music. Okay, so material Ka, Kd, Ks, these are your coefficients for ambient, diffuse, and specular. Okay, if you want a bit more control over your specular, you can set the specular exponent, N. Okay, so these come directly from Fong's lighting. Okay, and you can specular color reflectance. I don't really know what that means. I mean, the way I generated all those teapot images was using these commands, the different values of Ka, Kd, and Ks. Okay, so that's what you can do. Okay, like I say, it's not something I'm going to ask you to apply in the assignment. Okay, so that's Fong's reflection model. Are there any questions about that? No? Anything you're not sure of? Anything you want me to go over again? Have another look at the slide? No? Okay, very quiet. What if you can't have a negative light? You either have light or you don't. I mean, it's like area. You can't have a negative area. What? So if I hear the intensity, you just wouldn't have light. I mean, yeah. So the minimum value of I would be 0. Okay. You can't sort of suck light out of anywhere. I mean, this approximation is, if you talk to a physicist, they talk about sort of light bending and various things happening to light. We've got to assume, but light travels, and we've got to assume a simplified. Okay, anyone else? Okay, well, again, my apologies for finishing slightly early. On Monday, what we're going to be doing is looking at shading methods. So this model just looks for a single point in the screen space. We need to apply this across all points in the screen space.